Hello, I'm Robert Miles. Welcome to this recording of the Alignment Newsletter podcast. This is newsletter number 137, Quantifying the Benefits of Pre-Training on Downstream Task Performance, published on the 10th of February 2021 by Rohin Shah. Highlights. Link Scaling Laws for Transfer by Dani Hernandez et al., summarized by Asya. This paper studies empirical scaling laws for transfer learning in language models. The authors use transformer-based models to predict Python code by training on 3 different dataset curricula. 1. Training from scratch on Python code. 2. Pre-training on natural language, then fine-tuning on Python code. And 3. Pre-training on natural language and non-Python code, then fine-tuning on Python code. The authors then measure the effective data transferred from pre-training. If we want to replace all the pre-training steps with from-scratch training, maintaining the same loss, how much additional from-scratch data would we need? They find that when the amount of data used to train is small, effective data transferred is described by a simple power law function of df, the amount of data used for fine-tuning, and n, the number of parameters, k times df to the alpha times n to the beta, for constants k, alpha, and beta. In their experiments, beta doesn't change between pre-training on natural language and pre-training on a mixture of natural language and non-Python code. They hypothesize that beta measures how the model architecture generalizes on the target distribution and doesn't depend on the contents of the pre-training data. The authors think that alpha is a measure of the directed proximity of the pre-training and from-scratch distributions, with smaller alpha indicating closer proximity. Measuring alpha can be done cheaply by changing the fine-tuning dataset size while holding the pre-trained model constant, making it useful for deciding between collecting more fine-tuning data and increasing model size. For pre-training on natural language and fine-tuning on Python, beta is about 2 times alpha, so for decreasing loss, increasing the fine-tuning dataset by a factor of c, for example 100 times, would be worth approximately the same as increasing the model size by the square root of c, for example 10 times. The authors find that pre-training on a mixture of natural language and non-Python code has a higher k but lower alpha than pre-training on natural language alone. The higher k indicates that the mixture model has better transfer performance when trained in the low data regime, while the lower alpha value means that benefits of the mixture model diminish as more data is used. The authors also observe that 1. Not counting pre-training compute, pre-trained models are generally more compute efficient than from-scratch models when trained in the low data regime, about as compute efficient in the medium data regime, and less compute efficient in the high data regime, close to convergence. 2. Small pre-trained models perform worse than small from-scratch models in the high data regime. The authors call this phenomenon ossification, a term used to suggest that small pre-trained models may have a hard time moving away from bad initializations. And 3. In general, pre-trained models of a given size are compute efficient, on the frontier of loss given compute, for a large portion of their fine-tuning. From-scratch models, by contrast, are only compute efficient for a narrow window of training. Using too little compute for a given model dramatically increases loss, and suggests that you should instead be using a smaller model. This makes pre-trained models in some sense easier to train. If you want to read more, there's a Twitter thread by the user Hernandez_Dani. Asya's opinion. It's extremely cool to have a mathematical characterization of the power of pre-training. I'd love to see similar analyses measuring effective data transferred for tasks other than predicting the next token. If it turns out that modest increases in model size compensate for small datasets in a wide variety of tasks, that makes a strong case that unsupervised learning will be most of the work towards transformative abilities. Reading these scaling papers really makes me think that there's some deeper theoretical understanding of distributions and predictive models that these results are accessing, maybe encapsulated by this theory paper that I still haven't read. And there's a link to the paper A Neural Scaling Law from the Dimension of the Data Manifold by Sharma and Kaplan. Rohin's opinion. Like Asya, I really like the simplicity of the functional form of the scaling law, and the fits to the data seem quite good. I was quite surprised that beta seemed to be independent of the pre-training distribution. I would not have predicted that in advance. Note that despite the form of the scaling law, the effective data transferred isn't independent of the pre-training dataset size. That dependence effectively comes through the model size n. This is because the authors use compute-optimal pre-training, and so a given model size n corresponds to a specific amount of pre-training compute, which is probably almost the same as having a specific amount of pre-training data. I'm confused by the claim that distributions that are closer have lower alpha. It does make sense that for identical distributions we should have alpha equals 0. However, if closer distributions have lower alpha and beta is independent of the distribution, then as your fine-tuning dataset gets sufficiently large, you actually prefer the further away distribution. For example, once your fine-tuning dataset hits 10 trillion points, the scaling laws predict that you prefer to have pre-trained on text rather than 50% text and 50% code, which seems really bizarre. Possibly the scaling laws break down before that point, and in any case a fine-tuning dataset of 10 trillion data points would be ridiculously massive, but it still seems like something that needs to be explained here. Could we use this to improve timeline estimates? I take a stab at a calculation here, and there's a link to a comment by Rohin Shah on the Less Wrong post, Draft Report on AI Timelines by Ajay Kotra. The very rough and uncertain conclusion is that while transfer does seem to be a useful way to reduce compute requirements, the overall effect is not large. Section Technical AI Alignment. Subsection Problems. Link Challenges of Aligning Artificial Intelligence with Human Values by Margit Sutrop, summarized by Rohin. This paper argues that since immoral humans could use AI systems to do harm, we must build ethical rules into AI systems. For this purpose, the traditional notion of value alignment is not enough, as it only requires that the AI system do what the user wants, which might not be ethical. But we also cannot embed a single theory of ethics into an AI system, as there's no agreement on such a theory. Instead, we should focus on what we don't want an AI system to do, and rule out that behavior, while remaining uncertain or agnostic on what should be done. Rohin's opinion. I agree that successful AI alignment does not rule out the possibility of malicious use of AI systems. This paper is proposing putting rules inside the AI system that handle this problem, but as the paper itself notes, it seems quite challenging to even figure out what rules we would want. I personally am more optimistic about the alternate route, where we put rules outside the AI system to handle the problem. That is, we create laws and regulations around the use of AI, such that malicious uses can be blamed on the human operator, and enforcement mechanisms that ensure that we actually catch and punish such malicious uses. Subsection Preventing Bad Behavior. Link Challenges for Using Impact Regularizers to Avoid Negative Side Effects by David Lindner, Kyle Matoba, and Alexander Mullemans, summarized by Rohin. I'm not summarizing this literature review on impact regularization because we've covered almost all of the ideas previously in this newsletter, for example this blog post from newsletter 49. However, I do recommend it for its short, high-level introduction to existing ideas in impact regularization, as well as its ideas for future work. Subsection Handling Groups of Agents. Link Norms for Beneficial AI, a computational analysis of the societal value alignment problem by Pedro Fernandez et al., summarized by Rohin. This paper presents a simple quantitative model to argue for the following two observations. 1. Unless they're willing to fall behind others, individual actors will need to use AI systems to stay competitive. 2. Those AI systems will optimize for their owners' goals, even though a better outcome could be achieved if all AI systems optimized for the average welfare across all actors. Subsection Miscellaneous. Link Distinguishing Claims about Training versus Deployment by Richard Ngo. One story for AGI is that we train an AI system on some objective function, such as an objective that rewards the agent for following commands given to it by humans using natural language. We then deploy the system without any function that produces reward values. We instead give the trained agent commands in natural language. Many key claims in AI alignment benefit from more precisely stating whether they apply during training or during deployment. For example, consider the instrumental convergence argument. The author proposes that we instead think of the training convergence thesis. A wide range of environments in which we could train an AGI will lead to the development of goal-directed behavior aimed towards certain convergent goals, such as self-preservation. This could happen either via the AGI internalizing them directly as final goals, or by the AGI learning final goals for which the goals are instrumental. The author similarly clarifies goal specification, the orthogonality thesis, fragility of value, and Goodhart's law. Link Putting the Humanity into Inhuman Systems. How Human Factors and Ergonomics Can be Used to Manage the Risks Associated with Artificial General Intelligence by Paul M. Salmon et al., summarized by Rohin. This paper argues that the methods of human factors and ergonomics, HFE, could be applied to AGI safety. They list 15 different methods from the field, typically used to analyze the performance of humans in systems, which could be applied to AGI instead, on the assumption that AGI will be more like humans than like machines in today's systems. They then give examples of how these might be applied to the Prometheus story in the prologue of Max Tegmark's book Life 3.0. Rohin's opinion. I'm not very familiar with this field, but among other techniques, the paper mentions STAMP and STPA, which we've previously seen in Engineering a Safer World in newsletter 112. It does seem to me like these techniques would be useful to apply to the entire socio-technical system, of which an AGI system is just one part, and this is what the paper's examples do. It's less clear to me whether it makes sense to take techniques designed for humans and apply them to AGI. Perhaps we'll have enough understanding of the differences between humans and AGI that we could do this in a reasonable way, but I think there's a real risk that the methods give incorrect conclusions simply because they make incorrect assumptions about how AGI works, given that they were designed for humans. Nonetheless, I do agree with the core claim of this paper that HFE is worth exploring. Link, The Challenge of Value Alignment, From Fairer Algorithms to AI Safety, by Yason Gabriel et al., summarized by Rohin. This book chapter provides an introduction to AI alignment from a philosophical lens. Section Near-Term Concerns, subsection Recommender Systems. Link, Beyond Engagement, Aligning Algorithmic Recommendations with Pro-Social Goals, by Jonathan Stray, summarized by Rohin. To decide what item to show a user, a recommender system needs to have some metric by which to rank items. Since this metric must usually be automated, it often contains in large part some operationalization of engagement. Unfortunately, this metric may not be able to differentiate between clickbait or extremist content on the one hand, and actually valuable posts on the other. In a workshop on the topic, participants brainstormed 5 main approaches for improvement. 1. Build better controls. Offer users more and better ways to control their feed. 2. Develop standardized survey-based metrics. Surveys should be able to get a significantly higher quality signal to optimize than engagement. 3. Pay users for better data, such as survey data. 4. Recommend feeds, not items. If we rank items individually, it's quite likely that all the posts of the same type, for example controversial posts, will get high scores. By ranking entire feeds, we can also optimize for the diversity of items within the feed. 5. Incentivize the creation of different feeds, so that users can choose which ones they prefer, all things considered. Link, What are you optimizing for? Aligning Recommender Systems with Human Values, by Jonathan Stray et al., summarized by Rohin. While the previous blog post focused on societal-level approaches to recommender systems, this paper looks at what can be done on a technical level. By analyzing existing case studies of improvements to recommender systems, some of which we've seen before, for example in newsletter 96, the authors identify a typical approach taken in industry today. First, engineers identify a problem with an already deployed recommendation engine, perhaps from user feedback or through monitoring. Second, they develop a concrete procedure to identify instances of this problem in the recommendations. A typical approach is to curate a dataset and train an ML classifier to identify these instances, though it's also possible to use manual review. Finally, the recommender system is adjusted to avoid the problem, for example by adding a term to the objective when training the recommender system, or by filtering its outputs based on the classifier's output. The authors then propose 4 high-level technical approaches to recommender alignment. 1. Develop better measures of what we want out of a recommendation engine, for example an operationalization of well-being rather than engagement. 2. Allow users to collaboratively design the recommendation engine, called participatory design. Rather than have a company decide on how to trade off between different objectives, allow the users to settle upon the appropriate trade-offs themselves. 3. Interactively learn about the user's values. While this could look like building better controls, as suggested in the previous post, it could also involve, for example, using inverse reward design from newsletter 69 to maintain appropriate uncertainty over what the user cares about. 4. Design around time well spent, as evaluated by users on reflection or after consideration, rather than revealed preferences or immediate judgments. For example, we could show users a summary of their activity over the past month and ask how happy they are about it. If you want to read more, you can read Aligning AI Optimization to Community Well-Being, an expanded version of Aligning AI to Human Values Means Picking the Right Metrics, from newsletter 96. Rohin's opinion. Both this paper and the previous post seem like meaningful progress in ideas for making recommendation engines better, though as a caveat, I don't follow this space and so don't know to what extent this has been said before. I'm glad that we're getting to the point of actually proposing technical solutions. I hope to see more papers implementing such solutions. We've seen one from Twitter recently, in newsletter 123. This concludes Alignment Newsletter number 137. For more information, you can go to rohinshah.com/alignment-newsletter, where you can find all of the previous newsletters and also a spreadsheet of all of the papers and summaries that have ever been featured. Thank you for listening.